we can use the acid dissociation constant to determine the pH of a solution. In this example, we know that the initial concentration of acetic acid is 0.30 moles per liter. Let's write down the equation for acetic acid dissociation in water. Acetic acid is C2H3O2H. In water, it will dissociate to make hydronium ions and acetate ions, C2H3O2-. The acid dissociation constant for this reaction can be written as H3O plus times the concentration of acetate ions, C2H3O2-, divided by the concentration of acetic acid in solution. Now, in order to know the pH, we need to know the concentration of hydronium ions, which means again that we need to create an ICE table. So we have three compounds of interest. We have acetic acid, C2H3O2H, hydronium ions, H3O+, and acetate ions, C2H3O2-. So the ICE table looks at the initial concentrations, the change in concentrations, and the equilibrium concentrations, ICE, ICE. So we are given the starting concentration of acetic acid, which is 0.30 molars. We have no hydronium ions and no acetate ions initially. So we are not given much more information. We do know that the change in concentration of acetic acid will be very small because this is a weak acid. So we can write down that the change in concentration, or the equilibrium concentration of acetic acid, will be very similar to the initial concentration. That still leaves us with 5 squares to fill in. From stoichiometry, we can see that the change in concentration of hydronium ions will be the same as the change in concentration of acetate ions, and will be the same as the negative change in concentration of acetic acid. So let's assign a variable. Let's say let delta H3O plus equal X. If we do that, we can fill that in the box, then we can say that the change in acetate ions will be also X, and the change in concentration of acetic acid will be negative X. Remember that the concentration of anything, let's do it with H3O plus, at equilibrium is equal to the original concentration or initial concentration plus the change in concentration. So this equals 0 moles per liter plus X, which is equal to X. So the concentration of hydronium ions and the concentration of acetate ions at equilibrium is X. Now we have the information that we need to determine pH. So equilibrium concentrations are what we will be working with here. Let's now write our equation again for the acid dissociation constant, but let's substitute X for the concentrations of H3O plus and acetate ions. So instead of Ka equals H3O plus times C2H3O2 minus, it will equal x times x over the concentration of acetic acid, which is 0.30. So Ka equals x squared over 0.30. And we are given a value for the equilibrium constant, or the acid dissociation constant, of 1.8 times 10 to the minus 5. Now we have one variable that we have to solve for. So let's isolate x. X squared is equal to 0.30. We multiply that out on both sides, times 1.8 times 10 to the minus 5. Or x equals the square root of 0.30 times 1.8 times 10 to the minus 5, which equals 2.32 times 10 to the minus 3 moles per liter. So 2.32 times 10 to the minus 3 moles per liter is the concentration of both hydronium ions and acetate ions at equilibrium. So let's go over to the bottom right-hand quadrant here and write that out, that the concentration of hydronium ions at equilibrium is equal to x is equal to 2.32 times 10 to the minus 3 moles per liter. Now it's very easy to calculate pH. pH equals negative log H3O plus equals negative log 2.32 times 10 to the minus 3. The pH of the solution is 2.63. So now we have used the acid dissociation constant to determine the pH of a solution.